Welcome to today's presentation on acoustic analysis of a DC motor using M+P analyzer. Thank you for taking your time out and joining the session. In the end, right after the presentation, there will be a questions and answer session, so please don't hesitate to ask any of your questions afterwards. An acoustically pleasant product creates value for your customers. It feels valuable, is evidence of good design, and complies to legal standards. In this presentation, you will learn about the acoustic analysis capabilities of M+P Analyzer to help you designing better products. At first, let me introduce myself. My name is Thomas Hoffmann. I'm Global Product Manager with M+P International. I have a background in mechanical engineering and especially in mechanics and dynamic signal analysis. Before we start, here's a short introduction about M+P International. We are offering you multi-purpose data acquisition hardware and software. You can use it nearly anywhere where you have the need to measure and analyze data. We provide turnkey solutions from small channel counts starting at 2 channels up to really large systems with hundreds and thousands of channels. Our products always fulfill their purpose of delivering you efficiently high data quality and analysis. We are a technology leader in various applications and market segments, for example in aerospace or automotive applications. We are proud on our global service and support network. You are never alone with M+P International. Our partners like ProWave here support you with our products because they know your application and your local needs best. Let's start on the topic. Acoustic analysis results in better products. Take a look at the top right. In a car, you don't want to have any rattling or squeaking noises affecting the passengers and the driver. Or in an electric vehicle, sirring or other high-frequency noises from the driving motors might disturb the passengers. By acoustic analysis, you can find the sources of those noises and do something against it. Also think about regulations for emissions from vehicles, planes, or in civil engineering. For example, in wind turbines, acoustic emissions are regulated by law. An often overseen fact is that noises, like the mentioned rattling or squeaking, can give hints to failures in your products or other things affecting structural integrity. For example, failures or cracks in components or materials. The quieter your products become, the more important acoustic analysis will get, because you can register those small changes when in an already quiet environment. In this presentation today, we are using the acoustic analysis capabilities of M+P Analyzer. M+P Analyzer is a software package for data acquisition, data analysis, and post-processing. It has a clear user interface, is easy to use. You can create customer-ready reports on the analyzed data, and we are really supporting a lot of applications here. Some of the most prominent applications include real-time FFT analysis, modal analysis, rotational analysis, and the thing we are using today, acoustic analysis. We are supporting M+P data acquisition hardware as well as hardware from other manufacturers like National Instruments. Let's have a look at the experimental setup we are using in this presentation. It's a combination of acoustic and rotational effects. The core part is a DC driving motor mounted on a metal plate. The motor has an imbalance, so it can excite vibrations. The speed of the motor can be measured by a tachometer with 500 pulses per revolution. To measure the vibrations of the plate, I mounted an accelerometer with the sensitivity of 10 millivolts per G on the plate. To measure acoustic data, there's a microphone with a sensitivity of 50 microvolts per Pascal. The whole data acquisition is handled by the M+P WIP Pilot data acquisition hardware. It's a compact and robust housing featuring 8 channels of data acquisition, so 8 input channels, 2 output channels, and 2 tachometer channels. It has IEPE support to support the vast majority of sensors and microphones on the market. It features a maximum sampling frequency of 204 kHz with a 24-bit digital analog converter. It has a triggerable safety shutdown as the main safety feature. And for the interfaces, you can connect it to your PC by Ethernet and USB. And for mobility reasons, we also have a battery option. The settings in M+P Analyzer will be discussed on this slide. Some pre-analysis showed that for the experimental setup, nothing is happening above 2 kHz. So we limit the highest third octave to have its center frequency at 2 kHz. For the rotation data acquisition, we will be driving the motor from 1000 RPM up to 5000 RPM. For the accelerometer data acquisition, I'm choosing a 6.4 kHz sample rate for the narrowband spectra with a resolution of each frequency bin of 0.78 Hz. You can see that all those settings are available in a clear tab structure and can be accessed one after another. The last setting is the saving box. Here I can choose which results I want to save in the end. And we are saving here spectrum, rotational order data, and for the acoustic analysis, specific loudness, transient loudness, and the octave spectra, which I will explain later. That's a really cool feature. Those checkboxes here, I'm using that very often. You can very quickly change the scope of your measurements just by clicking different analysis results for saving. Before going into action, there's something really important you should do before every measurement. That is calibrating your sensors and instruments. Calibrated sensors ensure your valid measurement data. M+P Analyzer offers an automated calibration routine for every sensor type, for example, accelerometers, microphones, or voltage sensors. Here, the microphone's datasheet gives us a sensitivity of 50 millivolts per Pascal. I typed that in the sensor table, and you can see it on the bottom left. The current sensitivities is exactly those 50 millivolts. The black box you can see there is a microphone calibrator that puts out a sine tone of 1 kHz at a level of 94 dB. I can configure this calibrator in the M+P Analyzer calibration routine. After switching on the calibrator, you can see the new sensitivity in the bottom middle rising until it reached a stationary state of 56.8 millivolts per Pascal. By a simple one click on a button that is not on the screen right now, it's more to the right, you can take this new sensitivity and write it automatically into your sensor table. So you always have the right sensitivity for your sensors. Finally, on this slide, you can see the actual test I will be talking about in this webinar. You can see our experimental setup from 2 slides before, but this time in the video. And also on the bottom right, you can see the screen of M+P Analyzer. As said before, the measurement range is 1000 to 5000 RPM in steps of 20 RPM. That's a really cool feature of M+P Analyzer. It offers you speed linear measurements and also time linear data acquisition. That means if you are choosing a speed linear acquisition, The resulting spectrograms will always be linear in speed and don't depend on how linear you actually turn up the speed. If you have a nonlinear speed curve, you can use the time linear data acquisition mode and you will have the actual speed curve that you have in reality. You can see in the video, I'm turning up the speed in steps using the POTI there. And on the bottom, you can see the actual speed on the bottom right. And in small, I'm not sure if you can actually read it, but in small, N plus P analyzer shows you which speed you have to reach next to continue the measurement. You can assess the data live, as you can see in the video capture. N plus P analyzer gives you always the live data, so you can already online check if everything is going right. The time history data that is recorded is online processed in a narrowband spectrum and the third octave spectrum here. I choose the third octave spectrum to have a better data analysis capabilities later, but you can also choose whole octaves and other fractionals. Depending on how dynamic your signal is, you can choose slow response filtering for not so dynamic data, and for fast changing signals, we also have a fast and even impulse response filtering. Let's dive into the results. At first, you can see here the spectrogram of the measurement you have just seen in the video. This measurement reveals several things. In lower frequencies, you can see clearly the order excitation lines that results from the imbalance of the driving motor. These are shown as clearly as straight lines coming from the low speed to the and growing to the high speed in frequency. In higher frequency ranges, starting at around 700 to 900 Hertz, you can see multiple resonance zones. Resonance zones always show as nearly vertical lines or vertical zones in the spectrogram, as you can see by the two zones I marked with the boxes there. In very high frequency range at around 2000 Hertz, you can see very broad resonance zones. The reason for that is that the order excitation lines are very closely spaced to each other in those high frequencies, so they excite a really broad range of resonance frequencies. You can see them hinted in the blue lines, the order excitation lines, and you can see how closely spaced they are to each other. A small fact in between that covers why do we use octave spectra in acoustics. In the spectrogram, you have seen a narrowband spectrum. That means each frequency follows in a fixed frequency step size. But in acoustics, you will often see octave spectra. Why is that so? The main reason for that is how humans hear. We hear in intervals of factor 2. What does that mean? That means if you have two tones, one at 300 Hertz and one at 600 Hertz, they will sound kind of similar. Everybody who plays a music instrument can relate to that. But most interestingly, two tones at 5000 Hertz and 10,000 Hertz will also sound similar. So you have those factor 2 between the frequencies that causes two tones sounding similar to humans. So we can say that octave spectra take the human sound perception into account. If we are taking the data we measured, on the top right you can see the narrowband spectrum, on the bottom right you can see the resulting third octave spectrum. You can see there that we have strong sound levels at around 100 Hertz and at around 150 Hertz, which we both can relate clearly to sound pressure peaks in the narrowband spectrum in the top right. A cool feature of the octave spectrum is at the same time that we can calculate an overall sound pressure level. M plus P analyzer does that automatically, and you can see that overall sound pressure level in the far right bar of the graph, and it shows us that we have something about 80 dBs overall sound pressure level. So it was fairly loud when I did the test here. Let's talk about human perception of sound. So we are drifting now from the raw data analysis using the spectrums to the psychoacoustic effects, how humans hear the sound and how loudness affects us. The perception of sound of humans is frequency dependent. In low frequencies, we are very insensitive to sound, where in mid frequencies, we are very sensitive, and going to higher frequencies, the sensitivity falls again. The human listening limit is about 20 kilohertz. So above 20 kilohertz, we can't hear any sound anymore. In animals, for example, dogs can hear frequencies up to 50 kilohertz. Probably you know those dog whistles people sometimes have to call their dog back. Humans can't hear it, but dogs respond very well to it. The human sound perception is a carefully optimized system. It's most sensitive in the frequency regions where we normally speak, which is between 300 Hz and 3 kHz. In the graphic, you can see the sound perception sensitivity. And as I just said, in the mid frequencies, you have the highest sensitivity indicated by the minimum points of the curve. So if you want to improve your products for your customers, it's beneficial if you don't only look at the spectrums and octave spectrums, but if you also look at the loudness, because that's how your customers actually perceive the sound of your products. The loudness is also dependent on the surroundings of your test. Like, for example, in which room your product will be used and tested. And it's also dependent on other psychoacoustic effects, like the tonality and the sharpness of your product's sound. The loudness is measured in a unit zone or phone. Engineers don't really like something like loudness because they can't put it into formulas. So as an approximation to loudness, we have the frequency weighting. I'm sure you've seen it before in acoustic analysis. For example, we have the A, B, C, and Z weighting. The frequency weighting can be applied to narrowband and octave spectra and only includes the frequency dependence of the human hearing. It doesn't include the psychoacoustic effects I mentioned before when talking about the loudness. The weighting functions serve as a more objective approximation to the human sound perception. It doesn't cover the nuisance of sound. When we are comparing the third octave spectrum of our measurement with the A-weighted spectrum, we can see that the low frequencies are weakened significantly while the mid-frequency are amplified. You can already see that you must be careful with weighted spectra because a weighted spectrum hides low frequency components. So if you have a supplier that isn't really honest with you and gives you an A-weighted spectrum, you should be careful because in that low frequency range there can be hidden something. So as a practical tip, always ask for the unweighted spectrums. For example, by using M plus P analyzer for your applications, you can wait or apply the weighting functions afterwards. Now we are coming to loudness. So we are actually looking at how I, in my test facility, perceive the sound of the test I showed you before. The specific loudness is the perceived volume, perceived by humans. The loudness has an own frequency scale that is called the Bark scale. The Bark scale is a nonlinear scale that models the perceived pitch. So the Bark scale is modeled after the physical properties of the human ear. If we are comparing those two spectrograms, in the top right is again the narrowband spectrum you've seen before, and in the bottom right is the loudness spectrum over the Bark frequency scale. You can see that the loudness spectrum, it's much more blurry, indicating those psychoacoustic effects I mentioned before. The human ear cannot distinguish between the multiple excitation orders, especially in the low frequencies. You can see in the narrowband spectrum. So to humans, the narrowband spectrum will sound blurry, which is indicated by the loudness spectrum in the bottom right. So the loudness spectrum gives you a much better approximation how your product's acoustics will sound to humans or to your customers. Also, another analysis option we have is the transient loudness. The transient loudness is more useful for highly dynamic acoustic machines, like if you're having really fast run-ups or run-downs of some motors. The transient loudness additionally takes the temporal masking effect into account. Temporal masking is when you are perceiving a really loud sound followed by a really quiet sound. You can't hear that quiet sound because your ears are some kind of overloaded from the loud sound. And the transient loudness takes that into account. All those colorful spectrograms you've seen in the last slide might be difficult to assess quickly and get the right information from. So you have the option to calculate the loudness time history. That loudness time history combines all those spectrograms into one single graph you can see on the right. That graph allows for much quicker assessment of the overall loudness for each time step or for each speed. To get this graph, the loudness spectrogram is averaged for each RPM into a single value and then plotted over RPM. Here we can see a clear sharp peak at around 1,800 RPMs, which is some kind of resonance, and then a growing loudness over speed, resulting in a really loud zone at around 4 to 5,000 RPM. So actually the test I've showed you was loudest above 4,000 RPM. In the last slide, before the questions and answer session, I want to give you some examples of more advanced sound quality measures M plus P analyzer can give you. For example, we have warble analysis. Warble is a term for pulsations with frequencies of around 2 to 8 Hertz. They are often prominently in electric motors, so especially useful for electric vehicle analysis. Also, we have pitch analysis that is really useful for finding the fundamental frequency in a signal. Sometimes you have an overlay of multiple tones in a single acoustic measurements, and if you want to find The fundamental frequency, the pitch analysis is really cool there, especially useful for finding squeak and rattle fundamental frequencies. Then we have tonality characterizations following the ECMA 74 standard. Tonality is a term for assessing how much single tones your acoustic data contains. Then we have different measures for sound power measurements. They are according to the ISO 3745 norm. And right now in active development are also the ISO 3744 and 46 norms. So we are always trying to be up to date there. And then as the last special application, we are offering you sound transmission calculations and impedance tubes if you want to analyze really small material samples to get really to the bottom of your acoustic analysis. That concludes my presentation. Thank you for listening, everybody. And now I'm open to any questions.